Welcome back everyone. So in this video today, we'll be going over series and parallel circuit. So let's first start off by defining what series and parallel really mean. So I have two circuit drawings. The one on the left is called a series circuit. And the reason why this is because in a series circuit, current can only flow in one direction. It leaves the battery right here. Let's just pretend this is a 9-volt battery. It's going to leave the positive terminal and it's going to travel clockwise around the circuit like this and make its way back to the negative terminal. So this is the negative side of the battery. This is the positive side. The way you can tell is that the longer leg of the battery is the positive side, the shorter leg is negative. And this is what we would call conventional current. Conventional current goes from positive to negative. However, electrons prefer to flow in the opposing direction, so just opposite of conventional current. It would just go counterclockwise in this situation. So over here, we have a parallel circuit, which allows current to flow in multiple different pathways. So in this case, current can flow from the positive terminal of the battery, and then it has two choices. It can split off and go down this resistor right here, keep going straight, and then go down the other resistor. The current flowing through each of these resistors will eventually make their way back to the negative terminal of the battery, which is shown here. And once again, we'll just pretend this is a 9-volt battery. Also, as you add more resistors in parallel, that actually ends up increasing current because the same voltage from the battery is being supplied to all these resistors here. So as you add more resistors, or imagine they are light bulbs instead, it would take a lot more current to light up every single one of them, which is why current goes up as resistance decreases when you add more resistors in parallel. For a series circuit, as you add more resistance, current will go down, so it's inversely proportional. So now let's go over some formulas associated with series and parallel circuits. So for a series circuit, to find the total voltage, you can use this formula here. It's V equals V1 plus V2 plus V3 plus Vn. And what this means is it's taking the sum of all the voltage drops across each resistors in the circuit. So to find the voltage drop, we can use Ohm's law, which I covered in the previous video. So if you guys are interested, you can go check it out. I'll have it linked in the cards in the description. And so Ohm's law states that the voltage is equal to the current times the resistance, and in this case, since we're taking the sum of all the voltage drops, it will be the total resistance, or sometimes you might see it as Req, which just stands for equivalent resistance. Both of these are kind of used interchangeably. The only thing is that how you calculate it depends on whether the resistors are arranged in series or parallel. In a series circuit, the total resistance is pretty straightforward. All you do is just add up all the resistance using this formula right here. Since the current flows through each resistor one after another, the resistance adds up over time to contribute to the overall resistance. Now, let's try out this problem. What kind of circuit do you guys think this is? Is it a series or a parallel circuit? Well, if you said a series circuit, you would be correct because current can only flow in one direction. It goes from the positive terminal of the battery and travels in this general direction. So right now, we are given that the voltage is 9 volts and the resistance is 3 ohms, so therefore this calls for Ohm's law. And we're trying to solve for the current, so it's just the voltage divided by the resistance, and we can simply do some simple substitutions. So our voltage is 9 volts, resistance is 3 ohms, and when you divide volts by ohms, you get amps. So in this case, we have 3 amps of current, so hopefully that makes sense. Now moving on to our next example. So here's another example of a series circuit with multiple resistors in series. So as you can see here, we have 3 resistors, which I labeled R1, 2, and 3, and they each have their own resistance value. So to find the total resistance, it's simply just the sum of all these. So the total resistance, which is simply be 4 plus 3 plus 5, which is going to be 12 ohms as our total resistance. And once we have that, we can use Ohm's law once more. So to calculate the current, we use this formula, V equals I times the total resistance, and just start replacing these variables with their respective values. So 18 volts on the left side, and we're trying to find the current, and RT is 12 ohms, so now we have to divide both sides by 12, and you should get 1.5 amps for your current. Now, since we have multiple resistors in this series circuit, we have to take the current that we got and multiply it by each of these individual resistor values. So if you take 1.5 and multiply by 5 ohms for resistor 1, you should get 7.5 volts. So that's going to be the voltage drop across resistor 1. And if we do the same thing with resistor 2, that would be 1.5 amps times 3 ohms, which is going to be 4.5 volts. And if we take 1.5 times 4 ohms for resistor 3, we should get 6 volts. And the sum of all these volts will lead us back to the voltage of the battery, which is 18 volts in this case. So I'm going to draw an arrow pointing this way. Hopefully this isn't getting too messy, but if it is, feel free to back up the video to follow along and understand what these arrows are actually pointing to. But anyways, let's move on to our next example. But anyways, solving these circuit problems is kind of fun, so let's try some more problems. Okay, so over here we have a parallel circuit, and let's see if you guys can try and tackle this problem on your own. Pause the video and give it a try, and once you have the answer, unpause and I'll walk you through on how to solve. Okay, so hopefully you figured out the answer. If not, the first thing you want to do is identify that this is a parallel circuit, so meaning these resistors are in parallel. So to find the equivalent resistance, we would need to use this formula. It's 1 over R1, so essentially the reciprocal of the resistor value, and you're summing that with R2 and then taking the inverse of it. So that would be 1 over 5 plus 1 over 4, and then take the inverse of that, and that will be your equivalent resistance, which you should get 20 over 9 according to my calculator, which comes out to just 2.22 repeating. So this is the equivalent resistance for these two resistor values. It represents basically the same value, just more concise. So now that we have that, let's redraw our original circuit. So we're going to redraw it like this. We're going to keep the 12 volt battery and draw it as a circuit with only one resistor now, and give it the value of 2.22 ohms, which is what we found over here. And now from here on out, all we have to do is use Ohm's law once more. So it will just be V equals IR. We're solving for the current again, so it's I equals V over R. So we just do 12 volts divided by 2.22, and that should give us 5.4 amps for our current. So we have 5.4 amps of current flowing through this circuit. It's going through the 2.22 ohm resistor and then making its way back over here to the negative terminal. So now if we take this current value into consideration for our original drawing that we have up here, we can use that to calculate how much current is being split off into each of these resistors by using something called a voltage divider. So this is how our voltage divider would look. We would draw a line out like this, and then draw our resistor 1, which was 5 ohms, and then let's connect it with resistor 2. We set to 4 ohms, and we have 5.4 amps of current flowing to this voltage divider, and as the name suggests, it's dividing how much current is going to each of these resistors. So to find I1, which is the current flowing through R1, we have to use the formula R2, which is the other resistor, over the sum of R1 plus R2, and then once we have this quotient, we want to multiply it by the total current, which is I2. And to find I2, it's basically the same as I1, except place the numerator with R1. And once again, we're going to multiply it by the total resistance, or rather current. I1 is going to be R2, which is 4 ohms, over 4 plus 5 times the total current, which is 5.4 amps. So that's going to become 4 nines times 5.4 amps, which will give us 2.4 amps of current flowing through R1. So we have 2.4 amps going this way. So as you might guess, all we have to do to find how much current is going through R2 is to simply subtract these two values. So 5.4 minus 2.4 will give us 3 amps of current flowing through the 4 ohm resistor for R2. But just to verify that, let's show the work anyway. So using the formula we had, it's I2 is equal to the resistance of R1 over the sum of both the resistors, which is 4 plus 5 times 5.4 amps, which is just going to be 5 ninths times 5.4 amps. And as you can see, it does indeed evaluate to 3 amps. So these values are in agreement with each other. They indeed do add up to 5.4 amps, which is our total current. So that's correct. Now let's try out one more example before we end it off with the video. So in this example, we have a more complex version of a parallel circuit. We have 3 resistors this time in parallel, so we're just going to simply take the reciprocal of these resistance and then take the inverse of those summation of the values, and that will give us our equivalent resistance. So Req will just be 1 over 10, because that's the value of resistor 1, plus 1 over 2, plus 1 over 4, which are the other, and once we have the sum of those, we just want to take the inverse of them, and if you type that into your calculator, you should get 20 over 17, which is going to come out to be approximately 1.176. I'll round to the nearest 3 decimal places just to have some precision. So that's our equivalent resistance value for all 3 of these resistors. So once again, we're going to redraw this entire complex circuit in a more simple fashion. So we have the 9-volt battery here, and our equivalent resistance, which we found to be 1.176 ohms, and let's just close off the circuit, give it the negative terminal, and now once again let's use Ohm's law. So it's going to be V equals I times the equivalent resistance, which is Req. So 9 volts is our voltage, and we're looking for the current. We know Req is 1.176 ohms, so what we have to do is just divide both sides by 1.176 ohms, and if you type that into your calculator, you should get approximately 7.653 amps, and that's the current flowing through this particular resistor. So if we go back up, we have 7.653 amps flowing through this resistor. And to verify that this is the right answer for the original drawing, let's actually try and calculate the voltage drop across each of these individual resistors right here. So by definition, in parallel circuits, the voltage is always constant across all the electrical components, whether that be resistors, capacitors, inductors, or whatever electrical components you're dealing with. So we can use this formula here. So we know that V1 is equal to I1 times R1. So this might look a little familiar actually, because this is just Ohm's law with subscripts, of course. So we know the voltage is going to be constant, which we were given 9 volts, and the current we don't know what that is because it varies depending on how much resistance there is, and R1 was 10 ohms, so if we divide both sides by 10 ohms, so you'll see that the current flowing through resistor 1 will be 0.9 amps. And to find the current flowing through resistor 2, we just do V2 equals I2 R2. So once more, it's going to be 9 volts is equal to I2, because that's what we're solving for. And we know R2 was, what was R2? Let me scroll up real quick. It was 2 ohms. So if we divide both sides by 2 ohms, we'll get 4.5 amps for I2. And lastly, let's solve for R3. So we're going to use V3 equals I3 R3. So we have 9 volts. We don't know what I3 is. And R3 was 4 ohms. So if we divide both sides by 4 ohms, we'll get 2.25 amps of current flowing through resistor 3. So to verify that our answer is correct, let's just add up the current flowing through all these resistors. So it's going to be I1 plus I2 plus I3, and that is going to give us IT. So if we scroll back up, you'll see that we got 0.9 amps for I1 and 4.5 amps for I2. So let's plug that in. So 0.9 plus 4.5 plus 2.25, and that'll give us 7.65 amps, which is off slightly just because of rounding issues, but that's basically the right answer right there. So that confirms our work is correct. I hope you guys enjoyed the video. Let me know what kind of content you'd like to see in the future. If you want more electrical engineering topics like this, let me know in the comments below. So yeah, thanks for watching, and I hope you found some value out of this video today, and I hope you have a great rest of your day.